Let's take a look at chapter 10 on the correlation regression. We're going to concentrate on simple linear regression. So using linear equation to model the relationship between two variables. So we concentrate on finding the relationship between two quantitative variables without being able to infer the causal relationships. Correlation is a statistical technique used to determine the degree to which two variables are related. So we try to determine the strength and also the direction of the relationship. So we start with two variables, one of them called independent variable, the other one called dependent variable. So dependent variable and the independent variable. We try to figure out the relationship between those two variables. Now, the most important thing, most useful tools we can use to understand the relationship is called Scatterplot. So put into the Cartesian system with a rectangular coordinate, we have two quantitative variables. X represent the independent variable. Independent variable go to the horizontal axis, and dependent variable goes to the vertical axis. And then points are not joined, so we get a different kind of points scattered around, and we do not have frequency tables here. For example, let's say we try to use the weight to make prediction about the systolic blood pressure. Use weight to predict systolic blood pressure. SPP represents systolic blood pressure. So obviously a weight is independent variable. Systolic blood pressure is the dependent variable. So weight is independent variable. Systolic blood pressure is dependent variable. So systolic blood pressure depends on the weight. Now first of all, we plot this, so each one of these becomes order pair. So first order pair will be 67, 120. Second order pair 69, 125. Third order pair 85 and 140. Etc. Eventually you get on the last order pair 85 and 130. So each one of these order pair becomes a point on the scatter plot. So 67, 120, this first order pair here is 67, 120. The second order pair is 69, 125. And this order pair right here, 114 with the 200 approximately. So it's very easy to get in any technology or software. I'm going to show you later, how to create a scatter plot in Excel. So this scatter plot, as you can see, as the weight increases, then systolic blood pressure tends to increase. and SBP tends to increase. So this is what we call a positive or direct correlate relationship between those two variables. And if you're using a model here to modify this, to model this, we can use linear equation to model this. So this linear equation categorizes the essential characteristics of the regression model. Yeah, this is what we try to do here. Eventually we come up with the best fitting line. This line is called best fitting line to describe the relationship between those two variables. Now we're going to have a formula to calculate the slope and the y-intercept in terms of the best fitting line. So best fitting line, predicted y value equal to b0 plus b1 times x. Okay. And get there. Okay. So Scatterplots give us a pattern of data and typically indicates three types of relationship. First one is positive relationship, meaning x increases, then y increases. So x and y move in the same direction. Second type of relationship is negative relationship. X increases, then y decreases. This low relationship is no matter how x changes, y does not change correspondingly. So, random relationship. So, and let's take a look at some example on the positive relationship. As the number of hours spent studying increases, then the final grade in the course increases as well. So we have the general return here. As number of hours spent studying increases, the final grade also increases. So we call this positive or direct relationship. Another example, as age in weeks increases, then the height in centimeter increases. The height increases as well. So this is again is positive relationship, positive direct relationship here. And we also have a negative relationship as age of the car increases. Let's go over trend look like this. As age of the car increases, then reliability also decreases. This is negative or indirect relationship. And this graph shows no relation, meaning as the pulse rate increases, weight doesn't increases or decreases accordingly. So you see a random plot here. It's pretty random plot. We couldn't figure out any like clear pattern here. No clear pattern, so definitely there's no relationship between the pulse rate and the weight. There's no relation. So correlation coefficient is a statistics index showing the degree of relationship between a variable. It shows the strength and direction at the same time. Simple correlation coefficient R. I'm going to concentrate on this. It's also called Pearson's correlation or product moment correlation coefficient. Pearson's correlation coefficient measure nature and strength between two variables of the quantitative type. Again, we concentrate on quantitative variables. And the sign of R denotes the nature of the association, so either it's direct or indirect, positive or negative. The value of the R denotes the strength of the association. It could be a strong relationship, median and weak. Median relationship, weak relationship. The fourth one is no relationship. The sign is positive, that means the relation is direct. Positive, so increase in x values will result in increase of y values. Decrease in x will result in a decrease in y. If the sign is negative, that means as x increases, then y decreases. X decreases, y increases. So they move in the opposite direction. That's why it's called inverse or indirect relationship. The variable R goes between -1 to 1. The negative sign between -1 to -0.75, that's strong correlation. Between -0.75 to -0.25, that's intermediate or median. Between -0.25 to 0, that's weak correlation. Again, it's exactly symmetry right here. On the positive side, follows similar pattern between 0 to 0.25. That's a weak correlation. 0.25 to 0.75, that's intermediate correlation. 0.75 to 1, that's strong correlation. If you see -1, this is perfect correlation, perfect negative, perfect indirect correlation. Positive one indicates positive direct correlation. And if I equals 0, then there's no relation. I equals 0, no relation. No association or correlation between the two variables. Ups value of R greater than 0, less than 0.25, weak correlation. Between 0.25 to 0.75, intermediate correlation. 0.75 to 1, greater or equal to 0.75, less than 1, that's strong correlation. I equal to 1, that's perfect direct correlation. And we have a formula to compute this. We are given the x coordinate, the y coordinate, I need to create 3 other columns, which is product of xy, x squared and y squared. So throwing all the xy values, create a column, another 3 columns. You're gonna come up with a summation of xy, summation x, summation y, summation x squared, summation y squared. So once you have the 5 column created, sum up each column, get the total, and throw into the formula to get R. And for example, let me say a sample of 6 children was selected, and data about their age in years and their weight in kilograms was recorded as shown in the following table. It's required to find a correlation between age and weight. So as you probably figure out, age is an independent variable, this is x variable. Y variable is weight. So weight depends on the age of the child. Now we have given x and y values. Let's try to make sense of this. Weight depends on age. Okay. That makes more sense. Now in order to find out a simple correlation coefficient R, we need to create a table, come up with each column. So right here, this is the standard procedure. These are the x values, or the y values. Get the xy, meaning multiply x by y. Get it. First one is 84. 7 times 12 is 84. 6 times 8 is 48. 8 times 12 is 96. 5 times 10 is 50. 6 times 11 is 66. 9 times 13 is 117. And we also need to create a x squared. 7 squared turn out to be 49. Okay, 6 squared is 36. 8 squared is 64. 5 squared 25. 6 squared 36. 9 squared 81. Now y squared is square each one of the y values. First y value is 12. 12 squared is 144. Let's see here. A squared, that's 64. 12 squared again, 144. 10 squared, that's 100. 11 squared, 121. 13 squared, which is 169. After you create each one of these cell, then you sum up the x values. Sum up all the x values, you get 41. Sum up all the y values, you get 66. Sum up all the xy, you get 461. Sum up all the x values, you get 291. Sum up all the y values, you get 742. Now just plug into the formula. Now we get this, n times summation of xy minus summation x times summation y divided by square root of n times summation x squared minus summation x squared times n times summation of y squared. You can easily look up the formula in the formula sheet. And number of data values here is 6. That's 6 children. Our sample size equals 6. We get all this number, throw it in, we get a simple correlation coefficient R. Okay. Maybe do in Excel. You first of all do the data entry. So you get all these x and y. Now we need xy. X times y, x squared, and y squared. I'm gonna format it a little bit. Center, bold it. Multiply x and y. First one 7 times. So here a cell number is B3 times C3. You get 84, right? Then once you have one of them calculated, apply the formula to the rest of them. Get all of that. Similarly for x squared, 7 squared, b3 squared. And get the first square term, highlighting, get all of the square terms for x. Y squared, you do c3 squared. Again, highlight it, drag it. Now you sum up each column. Do auto sum on top. 41 for first one, 66 for second one. $461 for third one, and 291. Now you apply the formula is n times equal sign n6 times summation of xy b9 minus summation x b9 times c9. And then we take the square root out. Divided by the denominator, you get a square root. First one, n6 times summation x squared 291 minus summation x 41 squared, and then multiply by the square root, another square root, n times summation of y squared minus summation y squared. Okay, and then close parentheses. Now here enter, you get a correlation coefficient turn out to be 0.7. If you run 3 decimal places, turn out to be 0.760. And then also you can use a shortcut to calculate R. You just do correlation, COREL. There's a formula, and highlight all the x values, just no title, just x values. Highlight all the y values, and then here enter. You get the same result, right? And that's how you use a formula to get the correlation coefficient R. Then one more time, the formula is equal COREL. It's abbreviation of the correlation. Okay, let's go back to our PowerPoint. As you can see, it's the same result as we have in the PowerPoint. And based on this, since R is greater or equal to 0.75, less than 1, we'll call this strong direct correlation. It's positive, so it's direct. Bigger than 0.75, that's strong direct correlation. And this is another example, the relationship between anxiety and test scores. Obviously, when anxiety increases, anxiety level increases, then test score decreases. You can also see from the data itself, high anxiety, low test score. Okay. So still we set up the table, do the prep work, test score decreases. So this is an indirect correlation, and decreases. So we do the prep work, get all these sum of x, sum of y, sum of x squared, sum of y squared, summation xy, step by step. Scale these total numbers, and then we plug into the formula. Then the R turned out to be negative 0.94. You can try on your own. And this is definitely what we call a strong indirect correlation. And now let's take a look at this exercise, matching the value of R to the graph. So again, there are two groups of them. First group is, this one is negative, or indirect correlation, definitely negative. The middle two are positive. Positive. Compare the plot A to plot D. Plot A is more consistent. That means this R value is closer to 1, closer to -1. So A should be corresponding with 0.95. Right? R here equal to 0.95, negative 0.95, because it's negative. And plot D will be R equal to negative 0.9. Okay. It's slightly less consistent, so the R is further away from -1. You look at middle two, again the plot B is more consistent. That means R here should be 0.93. Okay. More consistent graph here, concentrated here. Same thing here. This R value is closer to 1. And here it's a lot less consistent, so the R value is a lot smaller, R equal to 0.49. And basically, based on the graph, you'll be able to get a rough estimate of the simple correlation coefficient R. And second part of this is regression analysis. So regression, we use technique concerned with predicting some variable by knowing others. So we come up with the regression model, B0 plus B1 times X. Come up with the best fitting line. And then from there, we'll be able to predict the variable Y using the variable X for any given X values with the regression model. We're using variable X to predict some outcomes of variable Y. Tells you how much the value Y increases as a function of the value X changes. Correlation describes strength of the linear relationship between two variables. Linear means straight line. Using linear equation to capture the relationship in terms of linear equation. Regression tells us how to draw a straight line described by a correlation. So now, this is the very first example. We try to calculate best fitting line here for a certain set of data. So here regression line makes the sum of the square of the residual smaller than for any other line. So we try to minimize the residual, meaning minimize the distance from each point to the line, to the best fitting line. So whichever line gives us the smallest distance, we call this best fitting line. So sum up all this distance, sum up the difference, and then minimize the difference. Then that's how we come up with best fitting line. Total differences. So regression minimizes residuals. We call this residual. The distance between each point to the best fitting line is called residuals. So we're using this method called least square method. Procedure minimizes vertical deviations of the plotted points surrounding a straight line. We're able to construct a best fitting straight line to the scatter diagram points and formulate a regression equation here. So B0 is a summation y times summation x squared minus summation x times summation xy divided by n times summation x squared minus summation x parentheses squared. B1 is n times summation xy minus summation y times summation x over n times summation x squared minus summation x parentheses squared. So again, once you do the prep work, you can also easily find B0, B1. So regression equation describe the regression line mathematically. So we're going to come up with intercept and the slope. Okay. Now right here, this is what we call B0, this is B1. Okay. Corresponds to our example. And slope equal to changing y over changing x, the ratio of those two. And then B0 represent, this should be B0, represent the y-intercept. B1 is the slope. A sample of 6 persons was selected. The value of the age, x variable, and the weight is demonstrated in the following table. Find the regression equation and what is predicted weight when the age is 8.5 years. So we're still using the same data set, x value and y values. Then we come up with all these different totals. Total of x, total of y, total of xy, total of x squared, total of y squared. Then B1, we can easily find the B1 using the formula. That B1 turned out to be 0.92. B0 is 4.69. So regression equation, regression model is predicted y values. Y hat represent predicted y values. Okay, so 4.69 plus 0.92x. Again, we can easily get this in Excel. I'll show you in a bit. So now in order to predict, so we try to predict when x equal to 8.5 years, what is predicted weight for this 8.5 years old child. So you have a regression equation here. You just plug into the regression equation with the given x values. So it's 4.69 plus 0.92 times 8.5 equal 12.51 kilograms. And second one, predict the weight for age equal to 7.5 years old. Again, plug in the 7.5 into the regression equation, so come up with 11.59 kilograms. Now we get two order pairs. First one is 8.5, 12.51. Second one is 7.5 and then 11.59. Now you can just plot it on the Cartesian system, age on the horizontal axis, weight on the vertical axis. First order pair 7.5 and then 11.59. Get that? Second order pair 11.59. Second order pair is 8.5, 12.51. Okay, and two lines determine the straight line. 2 points determine the line. So you get a regression equation, regression line, and this is what we call a best fitted line. A regression model. Okay, so you can, once you have a regression equation, you can create as many order pairs as you want and plot a regression equation on a Cartesian system. Create a regression line by applying two estimated values for y against the x component and extend the line right and left. And again, we calculate R, which is 0.760. R squared is called coefficient of determination, very important term. It measures the effectiveness of the model. Measures the effectiveness of the model. or another way of saying this is how good the model is. So in this case, r squared equal 0.760 squared turned out to be 0.557. Turned into percentage will be 57.7%. That means in this case, 57.7% of variations in the dependent variable y is explained by the regression equation or by the independent variable x. In this case, 57.7% of the variable y, which is weight, is explained by the independent variable age. Okay. Now let me show you how to get all of these informations in Excel. First of all, once we have this, we can create a scatter plot in Excel. So highlight the data values, including the title X and Y. I'll go to Insert. You go down here, you're going to see a scatter plot. You get this scatter plot. And on top of this, you'll be able to pick a design. Get this, you can pick a design on top. So you pick this design. And right here we could do a couple of things. You can put in a title. Predict weight with the age. Also, if you go here, click on the plus sign, you can modify a lot of things here. Change the color, if you want to make it a bright color, you could do that. And next step, click on plus sign and go down there. You're going to see the trend line. Follow the direction arrow here and click on more options. And right here we try to fit a linear model here, so you can pick linear, and then you can set display the equation on the line. Okay, so you will show you B0, B1. Okay, you can also display the R square, which measures how good this model is. Display R square as well. Okay. So now, as you can see, this is what if you do it by hand, that's how you get it. But definitely you can do it in Excel. Let's use different color. And then sometimes if you're not sure, whether you have the right work, when you can use Excel to quickly check it. And that's how you get all of this regression model and also the R square, okay, in Excel. Okay, and that's pretty much it for regression analysis.